We're going to talk today about volumes of solids, and we're going to consider volumes of solids with constant cross-sections. And then specifically, we will begin with volumes of solids of revolution.
Did the video go up last night?
Around 9:30
okay.
on account of I was here working on robotics until 7:30, and then I had the baby caps video, and then I did yours. I was tempted to not even do yours, but anyway. Yes, there's some good stuff on that video. I discussed problems that are ambiguous, where you could do either vertically or horizontally, and the factors that might lead you to do one or the other. So I encourage you all to take a look at that video.
Like around 5, I was doing this, and I'm like, it's not here. So
Yeah.
I did it anyways.
Yeah, I just should go home
It
with
is?
one.
Okay. No, can't do that. Try the finger.
You can use my water bottle. Why?
Okay.
Is that why they had a delay today? Because of single-digit temperatures?
Yes.
Are you serious?
Mhm.
Well, think about it. Public school kids have to wait outside for the buses.
My
Yeah.
kids in
Yeah.
Colorado, they will go to school and there's like a foot of snow on the ground. It's like 5 below. Because they went to skip school because it was single digits, they would time to school.
Yes, but they also know how to dress for 5 below.
This is true.
That's already.
You need people here like Alex and shorts. So really,
Okay, so what I mean by constant, the word constant here means that the cross-sections of the solid are a constant shape, but not the same size. And a problem is usually posed in this manner. A solid has a base defined by the region y equals 4 and y equals x squared. The cross sections perpendicular to the y-axis are, let's make up a shape here. How about semicircles? Find the volume of the solid.
I got lucky. Her room was locked and the lights were off, and I ran into her in the hallway a little bit.
No.
And then she was like, I thought it was from ESL. I'm not sure how this happened.
There's a story, but I'll tell her third grade. Much better.
She was catching on the strands and markers. I don't know how you get across the
Nah, I don't do anything.
Okay. Find the volume of the solid. So, what we have here, first of all, is a base, and there will always be a base in these problems. And then second of all, we have some kind of shape defined for the cross-section. So let's talk a little bit of theory, first of all. And we can visualize our solid here. Here's the region R that defines our... And now what we're told is that the cross-sections perpendicular to the y-axis are semicircles. And we are going to go ahead and draw for ourselves a representative cross-section. When we draw the representative cross-section, we see that it has a height of dy, so we are committed to using y's for our volume finding. What does it mean that there is a cross-sections are semicircles? It means that if we were to take this cross-section out, we've got some kind of solid, and if we visualize it in 3D, it's going to look kind of like this, and then it's going to taper down like this. And it's going to be some sort of, we do it in sort of a stereo projection thing. It's going to, the solid's going to look kind of like this. And so what I'm doing here is I'm taking and slicing that with a mathematical knife and taking one single cross-section, and when I pull out that one single cross-section here, then my representative rectangle now becomes the bottom of that cross-section, and the shape of that cross-section is a semicircle.
the integral of the area, right?
Yeah. See if you can visualize that. Does it make sense what we're talking about here? I know my art is bad. So the question then is, how are we going to think about volume? And the way that we're going to think about volume is that we're going to say that these, if I literally have a semicircular shaped wedge, like so.
So.
This. So if I picture this guy in cross section, you can see that he is a very thinly carved semicircle with a width to it. I'm having trouble doing this in 3D.
Got it. It's cute.
Can you picture what I'm talking about
Yes.
here? Okay. And this fellow right here is not exactly conforming to the solid. However, it is very close. And we can say that the volume of this solid, which we might call delta V, is going to be equal to the area times the thickness, which in this case is delta Y. If I add up all of the pieces like this, then what I get now is a Riemann sum that covers all of the pieces here. And if I now let y, the size delta y, go to 0, then what I have is exactly an integral from first y to last y of area as a function of y dy. And my volume is going to be that integral right there. And this is our volume formula. If we're working with vertical rectangles, then we'll have area as a function of x times dx. Does the concept make sense? We begin with a basic area formula, which is a volume formula, which is volume equals area times thickness for a prism. And then we generalize that by allowing our area to be different for each piece. Yes?
I just have a general question. When you have a z-plane, so three-dimensional, is the function that is shown in the z-plane a function of x or a function of y, or can it be both or either?
If you have a three-dimensional scenario, then you can represent z as a function of x and y.
Yeah.
Right, because the two variables would presumably be independent of each other. If they're not, so if that's the case, then what you're going to get is some kind of surface, right? Assuming that z is a legitimate function of x and y, you'll have some kind of a surface. If z, x, and y are all controlled by one single variable, then what you're going to end up with is some kind of curve in space. How are we doing so far? Does the theory make sense there? Okay. Now let's see how the problem works out in practice. What we need to do is we need to identify from our base and from our cross-section two things. First, we need to identify the limits of integration, the first and the last y. The first y is going to be down here at 0. The last y is up here at 4. And second, we need to identify the area as a function of y. And that's going to depend in part on the shape and in part on proper labeling. So if I take a look at my cross-section here and label this point, this point would be labeled x comma y, right? And because the curve is symmetric, this point here is going to be labeled as negative x comma y. And the distance across here is the horizontal distance from negative xy to positive xy In other words, the width here is going to be equal to 2x. And because I am working in y, it is necessary that I replace x with what it is. What is x if y is x squared? The square root of y, that's right. That's right. Technically plus or minus, but notice that we have symmetry here, and also we are using positive x values here, negative x values. Right. So now what I need is an area formula for semicircles, and of course the area of a semicircle is 1/2 pi r squared. And I go back to my diagram to ask myself, what is the radius of my semicircle? Please remember that radius is not diameter, and so the radius is going to be root y. Which is really convenient. So that I can now write volume is going to be the integral from 0 to 4 of 1/2 pi times dy dy, which is a really easy integration. C over 4, which gives me 4 pi. Do you guys remember doing this last year?
Yeah.
Do you have any questions about it?
I haven't done enough problems to know that question yet.
Yeah.
Exactly.
Fair enough.
Yes.
Fair enough.
It
Then,
makes sense.
yeah.
Seems familiar.
I remember doing it. I just, all the little quirks that you get.
Okay. Fair enough. You guys will end up doing some problems tonight, and you'll know if you have questions tomorrow. One extremely common type of constant cross-section is a solid of revolution.
I wrote last night, a lot of them were symmetrical. I would do them and I would get 0 because so I'd multiply it by 2 just to I completely forgot about that.
Okay, so here we have a curve with a domain, and we take this curve and we revolve it about the x-axis. And when we do, it forms a solid, and our job is to find the volume of the resulting solid of revolution. I should be more precise, because when I do a curve, if I just have a curve and take it around, then we're going to end up with a hollow solid, right? And when you just end up with an outside surface.
Yes.
So let's make this an actual region, rather than, so the region defined by or bounded by the curve y equals sine x and the curve y equals 0. This is much better. Now I have an actual region with substance to it, and when I revolve it about the x-axis, then I get a solid of revolution here. Here's my region. And you can imagine taking this region around the x-axis, and when you do, you're going to get a sort of a football shape. And you end up with a solid of revolution. You end up with a solid with constant cross-sections, and those cross-sections are circles. And this will happen every time. I'd say that they're circular circles. They're actually circular discs, because they're not hollow. They aren't circle shaped. They are circular discs with substance to them. So just as we did with the other constant cross-sections, we are going to cover our solid with a large number of circular disks. And that large number of circular disks are going to have a total volume that will be approximately equal to the volume of our solid. And in the limiting case, as delta x goes to 0, the total volume will be exactly equal to the volume. Okay? So let's see what this looks like. Because my axis of revolution is the x-axis, I'm going to take a cut perpendicular to the axis of revolution. This always happens. Because perpendicular to the axis of revolution is going to give me constant cross-sections of circles. If I take a cut parallel to the axis of revolution, it gets really ugly really fast. Because the resulting cross-sections that I get are going to be like shapes like this.
Yeah, that's really weird. Ew.
Yeah, definitely not.
Lots of fees.
Okay.
No, thank you.
So the cross-sections perpendicular to the axis of revolution are disks. Notice that disks is spelled with a C. And I'm going to draw one of our disks here. Disk with a K is a computer disk.
He asked what this is. It's like, I think you throw in like,
You throw
Yeah.
the
Highland
Highland
games.
Island.
Yeah.
What? Discus.
I don't often watch the Highland.
You know that there must be like 15. All right. So here's my disk.
This guy? Yes.
And the little piece of volume that is represented by my disk is going to be equal to area times thickness, and in this case the thickness is delta x. And the area is always the area of a circle, which is going to be pi r squared times dx times delta x. And if I now set up a total volume, the volume is approximately equal to a sum from I equals 1 to n of pi times the radius squared times delta x. Notice that I've emphasized that the radius is going to be a function of x. So as I move across from x equals 0 to x equals pi, those disks are going to get larger or smaller. They're each going to have a different radius, and that radius will be a function of x. Okay? So that in the limiting case, the volume will be exactly equal to the limit as the size delta x goes to 0. Like this, which is in fact the integral pi times the integral r squared dx. And this is the classic disks formula, which is really just a cross-sections formula, right? It's just the integral of area dx. If you're going in terms of y's, and you have the same formula but in terms of y's. When would you go in terms of y's? When your axis of revolution is a vertical axis. You seem troubled by this.
Yes.
Tell me.
The Y thing just throws me off. So,
With a little bit of practice, I think you'll be okay.
yeah.
You'll have the classic Christine,
Oh.
and you'll be fine.
So this function is r sin x.
Yes, okay, so let's examine. The only tricky thing about this really then is finding the radius. And the radius is actually very easy if you remember that the radius is the distance from the axis to the bounding curve. That's it. It has to be, because the bounding curve goes around the axis, which means that the axis defines the radius. Well, that means I just need to go to the axis, which is y equals 0 right here, and I need to go to the curve, and I need to find that distance, and we do distance by subtraction. So the radius is automatically sine of x minus 0, which is equal to sine of x.
Are we doing washers today?
Nope,
Does
that's
this only, because the way that I remember it, I thought you always had to do top minus bottom. Is that only what is the, it's like the way I've seen it?
actually with
Big R minus
solids
R.
revolution, you never do top curve minus bottom
What was that for?
Wash.
areas. Yeah, watch last night's video.
I'm just getting confused, it's like, where am I going?
Yeah, that's a really good question. Notice that what resolves that question is always paying attention to the geometry. So if I have some region defined like so, and I'm looking for the area of this region, first I visualize a representative rectangle that's going to be one of the many rectangles that covers this region here. And I simply say to myself, what is the distance from here to here? Top minus bottom. So that the area is the integral from A to B of top minus bottom dx. Contrast that with our situation here, where we are going about an axis of revolution. That axis must be the thing that determines the radius. And therefore we have curve minus axis and never curve minus curve as the radius of our revolution.
So you always have to.
Always curve minus axis
That's
for,
the height.
for the radius.
For solids.
For radius, not so much a height as a radius. Yeah. Okay. So I've got the radius here, and so now I'm prepared to say that volume is equal to pi times the integral from first x to last x of radius squared dx. Now this is a pretty puzzle. How do I integrate sine squared dx? If you watched the video last night, you know. Anybody?
I've done the homework before you.
Yeah, we're going to appeal to the double angle identity for cosine.
I was gonna guess that.
Recall that
was kind of-
cosine 2x has three different representations. Cosine squared minus sine squared, 2 cosine squared minus 1, and 1 minus 2 sine squared x. All three of these can be converted to one another by substituting sine squared plus cosine squared equals 1, the Pythagorean identity. Well, these two here are very, very useful to us because they allow us to represent cosine squared and or sine squared in terms of cosine 2x. If I solve for sine squared x, everybody do that. Solve for sine squared x in the second. Go. And you should get that. So that we can replace in this integrand sine squared with what it is. And now we're going to integrate this term at a time. Like so. This integral is very obviously pi over 2. So that I get pi squared over 2 for this term. This integral right here is automatically 0. You say, why? Because cosine of 2x has a period of pi, and therefore the positive area here and the negative area here cancel out and give me 0 automatically. I mean, I could do that as sine 2x over 4 equals something like that. But let's appeal to the geometry and make their lives a little easier. Right? And so we get this volume as the volume of our solid revolution. See if we can squeeze in one more really fast here. Same region that we had before, y equals x squared and y equals 4. Find the volume of the solid generated when R is revolved about the y-axis. Okay. Please notice that here, our region exists on both sides of the axis, right? However, it is symmetrical, so that when I revolve it about the y-axis, what I end up with is a kind of bowl shape that looks like this. If it were not symmetrical, then we would end up with a really complicated solid, and we never work those problems, basically.
For the AP exam, would you have a problem like the last one where you have to have the angle identity to be able to solve the integral?
Certainly in old school days, yes. I'm not sure if that's true anymore. And so we're going to begin with a representative cut. That is, I take the cut. What's the key word for the cut here? Perpendicular to the axis. That's right. And here's my cut, like this. And my cut then defines a disk, like so. And I can say that here I'm going to represent this in differential terms. I'm going to say that dv is equal to pi r squared dy, just like that. In other words, a small element in volume is pi r squared times a small change in volume.
Teachers, pardon the interruption. The lacrosse meeting that will occur today at lunch is for the boys lacrosse team only. The lacrosse meeting at lunch today is for the boys lacrosse team only. Thank you.
Notice that my y's go from first to last y, just like this. And now the only trick is to find the radius. So I go back to my curve and I think curve minus axis. And this point is x comma y on the curve. And this axis is y equals 0. So the radius is equal to x minus 0. However, what is x? X is the square root of y, just like so. And then, the only Kara Davis that I know graduated about 10 years ago.
Nice.
No, there's a freshman.
No, Karen, that's Paige Davis. Paige Davis.
No, there's a Kara Davis.
Really?
Yeah.
There's another Kara
10
Davis.
years. Yeah.
Wow. Yeah, she's a freshman. She would not be.
She would not be in Cal. No.
She wasn't.
Oh, because had they switched, when we switched at the beginning of the year, we had English class.
They're like
Okay.
a couple months.
Karen Davis, Paige Davis graduated with Jessica.
This was the only thing that was even slightly confusing about this problem. So I want to make sure that everybody understands how I got there. Geometrically, I think to myself, this horizontal distance is going to be the difference of the x coordinates, right? So it's going to be x minus 0. And then immediately I know that I have to put it in terms of y because I am working in terms of y. Does that make sense to everybody?
You scroll up just a little bit.
Yep.
Yeah, that's what I expected. So that's how you got that.
Yes. How I got the 4. Yes. That was the top of that region. Carry this home. And we get 8 pi's the volume of our solid. Questions, comments, or jokes?
But I have a meeting with Curtis.
Please notice, by the way, that the volume of our solid of revolution was exactly twice as the volume of the solid from the first problem. Let's see why that was. This solid had the exact same region as the base, but its cross sections were what? What shape?
Semi.
Semicircles.
Semicircles.
Ah,
Solid of revolution, the cross sections are circles, duh, we get twice the volume.